Using genetic engineering, scientists can create cells that produce proteins they wouldn't ordinarily produce. For example, circular pieces of DNA, called plasmids, found inside bacterial cells, can be engineered to make such proteins as human insulin by inserting the gene that codes for that protein. Special enzymes called restriction enzymes, which recognize, bind to, and cut specific DNA sequences, are used to open up a plasmid in preparation for the insertion of a gene. Some restriction enzymes leave the DNA with uneven ends, also known as sticky ends, shown here. If the gene we wish to insert and the plasmid are both cut with the same enzyme, these sticky ends will be complementary, meaning they will readily bond with one another.
Going overnight, that's okay too, because our time-saver qualified enzymes show no degradation after an overnight reaction. A recommended protocol would be a microgram of DNA, a microliter of your restriction enzyme, 5 microliters of our 10x buffer, and up to 50 microliters of water. Digest for 5 to 15 minutes, add your loading dye, and load your gel. Make sure when you're doing the reaction to keep your samples on ice if they're not in the freezer, and make sure to mix well, pipetting up and down, flick the tube maybe, and spin down.
The first thing you should do is draw out your expected results. While this step may seem unnecessary, it's good practice and it will make your analysis go a lot faster. In this exercise, we would like to verify the identity of a plasmid we received from AdGene. We'll digest the 7.5 kilobase pair plasmid individually with either AGE1 or XBAL1, which are both single cutters, and then with AGE1 and XBAL1 together. We'll also digest the plasmid with EcoR1, which has 2 recognition sites in the plasmid. So let's draw out the expected results. Here's our gel. Lane 1 is the size marker, often referred to as the ladder. Lane 2 will be the undigested control. Because this plasmid is circular, the migration pattern of the undigested control diverges a bit from the migration pattern of the ladder, which was made with linear DNA. The uncut plasmid typically adopts a supercoiled conformation. That's because these plasmids were isolated from bacteria, and supercoiled is the native conformation of plasmids in vivo because it's compact. A compact conformation allows the plasmid to migrate through the gel at a faster rate than its linear equivalent. This is because it experiences the same amount of electromotive force, but less resistance due to friction. As a result, it runs a little smaller than the equivalently sized band on the ladder. This plasmid is 7.5 kilobases. So let's draw the supercoiled band right below the 7.5 kilobase pair mark. Another conformation of uncut plasmid DNA is nicked. DNA can be nicked naturally in vivo through the activity of topoisomerases. DNA can also get nicked during purification if the conditions are harsh. So it's common to see nicked DNA in your uncut control. When one strand of the DNA is nicked, supercoiling is released. So the conformation of nicked DNA resembles a floppy hula hoop or a hair tie, making it relatively large. In fact, nicked DNA is so big that as it's migrating through the gel, it experiences greater resistance due to friction than even the linear DNA, which can be more flexible than the nicked. Consequently, nicked DNA runs a little higher than the equivalently sized band on the ladder. Since we're still talking about a 7.5 kilobase pair plasmid, let's draw the nicked DNA a little above the 7.5 kb mark. Now that we've drawn our control, let's move on to our digestions. Lane 3 is the AGE1 digestion, which yields a single product. And because it's linear, its migration is consistent with the marker. So we expect to see a band at the 7.5 kb mark. Lane 4 is the XBAL1 digestion. Just like AGE1, it yields a single linear 7.5 kb band, so we expect to see a band in the same 7.5 kb spot. Lane 5 is the double AGE1 XBAL1 digest. According to our map, we would expect 2 products, a 7.2 kb band and a 300 base pair band. Since these 2 fragments appear in a 1-to-1 molar ratio, we know the 7.2 kb band will be 24 times brighter than the 300 base pair band, because it is 24 times as large. This means that if we don't have a bright enough 7.2 kb band, we might not even see the 300 base pair band. Lane 6 is the EcoR1 digest. EchoR1 cuts in two places, so we expect two products, a 5.4 kb band and a 2.1 kb band. Okay, this picture looks complete. Let's run our experiment and see our results. Run your gel long enough to get good separation of the bands. Don't rush it. Now that we've run our digestion, let's go through each lane and compare our experimental data with our expected results. We've marked the latter with the sizes of the markers. Lane 2, the uncut negative control. We expect to see a supercoiled band and a nicked band, and that's what we see here. As expected, the supercoiled runs a little faster than the 7.5 kb band, and the nicked runs a little slower than the 7.5 kb band. Based on the relative intensities of these two bands, we can tell that the majority of our DNA is in the supercoiled conformation. Also, based on the sharpness of the bands and the lack of smear, we can deduce that we have a clean DNA prep. Lanes 3 and 4 are the AGE1 and XBAL1 single digests, where we expect a single 7.5 kb band, and possibly some of the uncut fragments. In each lane, we do see a linear 7.5 kb band. Lane 5 is the AGE1 XBAL1 double digest, where we expect two digestion products. We can identify the 7.2 kb band clearly. Since this is a new band, we know it must be the 7.2 kb digestion product. Looking for the 300 base pair band, we find that it's visible but faint. From our earlier calculations, we expect this band to be 24 times less intense than the 7.2 kb band, so the band intensity is not surprising. Lane 6 is the EchoR1 digest. Again, we see two new digestion products in this lane relative to the negative control lane. Notice we do not see any residual nicked or supercoiled bands, which indicates that the reaction was run to completion. Overall, our gel looks close to the expected results, and we don't see any bands that we can't explain. This indicates that the plasmid we've isolated is most likely the plasmid we think it is.